Hey folks, welcome to part 3, acids and bases. We're going to finish up talking about strong acids and bases and get back to Le Chatelier's principle applied to equilibria. All right, so I got a picture of two different acids here. A car battery with multiple warnings on it and a bottle of red wine vinegar, also an acid. So both of these are acids. But clearly they're very different, right? Sulfuric acid in your car battery, you're going to want to stay away from that. The Pompeian red wine vinegar, you're going to want to eat that, right? So they are not the same, but they're both acids. So clearly there's a broad spectrum of what it means to be an acid. Strict definition donates protons, right? But there are different degrees to which acids can do that. So they're classified as either strong or weak depending on the extent to which they dissociate in water. What that means is the extent to which the acid donates a proton, right? So like a strong acid will dissociate completely and give away every single proton that it can. A weak acid, not so much. It'll give away some, but not all. So let's look at a kind of a diagram of this, an illustration. So across the top, we see a strong acid, hydrochloric acid, HCl, right? And so the H is a little white atom, Cl is the green atom, and we put that in water and look at what we get out. There are no longer any HCl compounds. We see just chloride and hydronium. That is, that it completely dissociated. There's virtually no HCl molecules left, and it is now just Cl minus and H3O plus. Excuse me. While we're here, we'll look at a strong base, such as NaOH, sodium hydroxide, right? Which has a sodium plus ion and a OH minus ion, polyatomic ion, and that will completely dissociate. And we see here no longer any NaOH next to each other. They've all completely split up. So we have ions, Na plus, we have OH minus, and we still have water molecules around. So there's virtually no NaOH left. It is completely dissociated into Na plus and OH minus. And strong acids and bases, by the way, because they completely dissociate, produce many ions in aqueous solutions, they are strong electrolytes. So let's look more closely at these. Strong acids dissociate in water completely to form conjugate base and hydronium ion. HCl, incidentally, is the only strong acid that's produced in the human body. Normally these are very corrosive, very, very problematic. HCl is gastric juices in your stomach. So they are safe to handle when they're diluted, but they're very highly corrosive when concentrated. And then strong bases are basically groups 1 and 2, 1A and 2A metals with hydroxide, completely dissociate in aqueous solutions to produce hydroxide ions and cations. They're strong electrolytes and, again, highly corrosive when concentrated. So luckily there's a short list of strong acids and strong bases, and these are it. If it's not on these lists, it's not a strong acid or a base, so it's considered weak. And you don't have to memorize this, right? You don't have to memorize it. Oops, so my box is kind of in the way. This one right here is supposed to be HI, hydroiodic. And so we have nitric acid, sulfuric acid, perchloric acid, and then some halogen acids. And all of the strong bases are hydroxide bases with various cations. So you don't have to memorize these. I'm just pointing out that it's actually a very short list of strong acids and bases, and everything else is weak, such as this, acetic acid. So here's the same kind of diagram, and notice that when we have equilibrium, there is some acetate ions, there are some hydronium ions, and there are also still some of the original acid that did not dissociate. So weak acids and bases are characterized by little dissociation in water. They produce few ions, they're weak electrolytes, and notice here, equilibrium sign. I don't know if you noticed before, but we had forward arrows, right? Because these were forward reactions, they didn't really go back. But now we're at equilibrium reactions with an equilibrium arrow. Generally, at equilibrium, there are more reactants than products, right? So they are K values less than 1, equilibrium constants less than 1, and so not very many ions are actually produced. Now, how many actually are can be quantified. We quantify the strength of an acid by measuring the amount of hydronium, H3O+, or sometimes we just call it H+, and we quantify that using pH, which is actually the next section. So here's another example of weak acid and then a weak base, and now we're going to pay attention to the fact that we have an equilibrium sign here. We did before, but we didn't really talk too much about it. So even though this is an acid-base reaction, right, most of what we see like at equilibrium would be still acetic acid, and there'd be only very little hydronium and acetate. And the same for the example down here. So anytime there's equilibrium, there's Le Chatelier's principle, right? Just as a quick review, Le Chatelier's principle says that when equilibrium is established, any disruption to that equilibrium will be counteracted by the system to find a new equilibrium. We talk about shifting the reaction one way or another. Right, so a reaction shifts in a direction that counteracts a disturbance. A shift to the right would be what we call when a forward reaction is enhanced, more product is formed. A shift to the left or to the reverse reaction, more reactant is formed, is what we call a shift to the left. So this is really important in weak acids and base reactions because they are at equilibrium, right? And this gets us back to our beginning example, right? Where we had carbonic acid and a biochemical pathway. So if we go back here now, remember carbonic acid now we've seen a couple times. It can be produced in the cells from CO2, and then bicarbonate, HCO3 minus, is regulated by the kidneys, and so this equilibrium can be maintained and controlled by the kidneys and by respiration in the cells. So the key here is the hydronium ion, right? This is acid. I'm going to measure this as the acid, and if there's too much hydronium, then the kidneys can pump up production and shift this way. If hydronium is too little, the kidneys can slow down production, which would produce more, and also we could decrease respiration and decrease this one. So you can act from either side. Anyway, we'll come back to this exact reaction at the end of the chapter and maybe a few times before then. But so I think you'll get pretty good at this as we see it again and again. But basically, this is biologically and physiologically a very important equilibrium, and your body has multiple ways of controlling it. It's really pretty cool. A pyruvic acid is also a weak acid, and here's the reaction for it. A couple questions. Number one, does an increase in pyruvic acid cause a shift to the left or a shift to the right? Okay, so if we increase pyruvic acid, right, we're going to shift away. So shift away from the increase, or shift away from the addition, right? So it's going to shift to the right, which will cause, what does that do to the concentration of the hydronium ion? It will cause an increase in the concentration of the hydronium ion. Now, number two, all the opposite, right? Decrease in the pyruvic acid will cause a shift to the left, because you move away or move towards the stuff that was taken, and that would consume H3O plus and cause the concentration of that to go down. All right, I've got one more question here, 3 parts, and we'll finish up with this. Okay, so ammonia, NH3, that's all we need to be told. It's a weak base. I want you to write the equilibrium reaction for ammonia in an aqueous solution. So in aqueous solution means with water. And then, if additional hydroxide ions are added, what will happen? Will the reaction shift to the left or to the right? And if some ammonia molecules are removed from the solution, what will happen? Will it shift to the left or to the right? So you can pause this and work through this for yourself, and then I will show you what I've got with this right now. So the equilibrium reaction would look like this. We have ammonia, water on the reactant side, and it will produce the hydroxide ion and ammonium ion on the product side. Now, if we add hydroxide, what happens? Adding hydroxide will cause a shift to the left, enhancing the reverse reaction. Now, if we remove ammonia, so this, we have less of this, will cause a shift to the left again to replace it. So, basic equilibrium stuff, but now applied to acids and base reactions specifically. Okay, so that wraps up section 1. In section 2, we'll go back to quantifying hydronium, or H+, and the strength of an acid with a pH value. So, see you then.